Start.
Well, today I will be explaining about the gas turbines and the Brayton cycle. So basically what we know about the Brayton cycle, that's the matter that I will be touching in to talk about that in detail. Okay.
Take 3.
Again lah.
No need to stop. Okay. Hello sir, my name is SHAKTIVELL, son of M.LETCHUMANAN. So today I will be explaining in detail basically on theoretical part of this gas turbine and the Brayton cycle. So basically the application of this gas turbine is like in jet engines or all kinds of, some sort like these kinds of engines. So these engines or gas turbines, they use Brayton cycle for valid reasons. So after this I will be talking about what from where does this Brayton cycle originates. So about the Brayton cycle. The Brayton cycle is a thermodynamic cycle named after George Brayton. So the Brayton cycle's name come after his name. So it describes the workings of a constant pressure heat engine and modern gas turbine engines and air breathing jet engines follow the Brayton cycle. Which means over here air breathing jet means the air that is being drawn in for the sake of the engine's propulsion, all these things. So the next I'll be talking about the variants in Brayton cycle. What are the basic Brayton? Brayton cycle. They are categorized. They varies in a lot of categories, and these are the four categories. First is closed Brayton cycle. Second is open Brayton cycle, and third is solar Brayton cycle and reverse Brayton cycle. And this solar Brayton cycle is it seems to be a bit interesting because the heat is being is absorbed from the sunlight itself, and from there the gas. From there Brayton cycle can be applied for this application. So this is the Brayton cycle. So I'll be touching in about the closed Brayton cycle, so it's easier for us to understand even more. So gas turbines are described thermodynamically by the Brayton cycle. In this cycle, what we know is the air is being compressed inside a compressor and it drawn into the heat exchanger where the heat is being pumped in, and the whole gas is being flowed inside the turbine, and it is being drawn into the heat exchanger for heat rejection. And we can see over here there are two tables, and I will be focusing in more on TS diagram, so it is easier for us to understand even more. So over here we can just see the comparisons with this diagram, schematic diagram and the TS diagram. So number one seems to be the compressor, where the pressure over here increase and it is drawn into the heat exchanger, and combustion occurs over here at a constant pressure, and over here in this region, in the turbine, the air expands. The air expands over here, and heat rejection occurs again. And this is considered a continuous cycle, and it is considered it's much more sufficient and efficient enough to support the to give a valid reason for us. Okay. So the next thing I will be touching in is about advantages of gas turbine engines. So very high power to weight ratio, more size efficient, moves in one direction only with fewer moving parts, and low operating pressures, high operation speeds, low lubricating oil cost and consumption. The reason is that why am I talking about the gas turbine? The gas turbine engines is because Brayton gas turbines uses the Brayton cycle. So Brayton cycle gives a valid proof for the usage of gas turbine in maybe a lot of applications. So these are the advantages, and there are some disadvantages too. And the disadvantages of these gas turbine engines are they are more expensive compared to a similar sized reciprocating engine, more complex machining operations, usually less efficient than reciprocating engine, especially at idle, and delayed response to changes in power settings. So these are the disadvantages, but we have to choose these gas turbines according to our applications. That because there are advantages and disadvantages over that. So thank you.
Good morning, my name is RUBINDREN and I'm going to explain about another problem that we are going to solve for today. Okay, which is in a BRAYTON cycle based power plant, the air at the inlet is at 27 degrees Celsius, 0.1 MPa. The pressure ratio is 6.25 and at the maximum temperature is 800 degrees Celsius. And what are we going to find for today is the compressor work per kilogram of air, the turbine work per kilogram of air, and the heat supplied per kilogram of air, and also the cycle efficiency. Okay, first from the question we get to know that the temperature 1 is 27 degrees Celsius and also the P1 is 0.1 MPa, where for the pressure ratio is 6.25 and also the T maximum is 800 degrees Celsius. Okay. As from the details that we have collected from the question, I have listed out where the temperature is already converted to Kelvin and also the P1 and also T3. Okay, this is the TS diagram for the question, and now I'm going to solve for the first process, where the process is isentropic. T2 over T1 is equal to compressor. As we know that 1.4 is the constant value for the air, and once we have solved it, we can get the value of T2, and for the work of the compressor, we use the formula where constant pressure T2 minus T1, and this is a constant value for air. Once we have solved it, we can get 207.72 kilojoule per kilogram for the compressor work per kilogram of air. Thank you.
Going to the next topic. So the next question is the turbine work per kilogram of air. Okay. So the same thing what we do for compressor work. So to find the turbine work, so the formula is Cp and T. So the turbine is here. So T3 minus T4. So in order to find the T4, we need to use the pressure ratio. So the pressure ratio is T3 minus T4, which is equal Rp K minus 1 over K. We already know the T3, the Rp, which is 6.25, the K is constant, we can get it from the property table, and we will get the T4. So the T4 is equals to 635.29 K. Okay. After we get this value, we just substitute into this T4. So the Cp is the specific constant, we can get it from the table A2. So the Cp is 1.005, T3 is 1073 minus 635.29, which is equals to 439.89 kilojoule over kg. Okay, we're going to for the heat supplied per kg of air. The heat supplied is the Q in, which is in the third point, and from the third point to second point. So it's the same thing like we do for the work done for the turbine compressor. But now we want to find the Q in. So Q in is equals to Cp, which is 1.005, T3 minus T2, which is 1073 minus 506.69 equals to 569.14 kg over kjoule over kg. Okay, the next is the cycle efficiency. We know the cycle efficiency is N, which is equals to W net over the Q in. W net is the work of the compressor, the turbine minus with the work of compressor over Q in. The following part we already saw for the turbine and compressor, just we need to substitute the value and we will get the cycle efficiency. For the work turbine is 439.89 minus 207.72 divided by this value Q in, which is 569.14. We will get the value 0.408, and in percentage value we must times with 100, so we will get 40.8%. That's all from us. Thank you.
Guys, my name is YUEN and I will be teaching you a tutorial on how to solve a problem, a Brayton cycle with regeneration. Okay, so as you can see, we extracted this problem from one of the universities, and we tried to do it. So we can see that this is a Brayton cycle and it's not stated ideal, so we can be sure that there will be isentropic efficiencies in compressor and also turbine. Okay, and stated this cycle produces 150 kilowatt kilowatt. So we can know is 100. The W dot net rate of W net is 150 kilojoule per second. And then it said inlet temperature of compressor is 293 Kelvin, while turbine is 1073 Kelvin. So T1, we can know T1 is 293 Kelvin, while T3 is 1073 Kelvin. Compressor has efficiency of 0.87, and while the turbine has 93%, means 0.93. Inlet temperature of regeneration is 10 Kelvin, less than turbine output temperature. So this information will be required when we are trying to solve points the points for when to try to answer the T temperature for the regeneration input and output. Okay, then consider pressure ratio 8, RP is equals to 8. Constant pressure specific heat CP is 1.005 kilojoule per kg Kelvin, and specific capacity, the coefficient of K is 1.4. So let's start, and the question asks us to determine the mass flow rate of the system, M dot, and rate of heat addition and heat rejection, Q dot and Q in dot and Q out dot. So let's start. Okay. So as you can see, the graph is already drawn on the board, and also the vital information has been extracted. So as you can see, just now, we know the generator input is the 10 Kelvin less than compressor output. So as you can see, compressor output is point number 4. Regenerator input is 0.5, and the shaded area here signifies the regenerated regen heat, safe heat. So firstly, we have to get the information for all the points. So we know this information, and we have the formula. So we are going to try to solve for T2S. T2S over T1 equals to RP K minus 1 over K. So T2S is 293 8 1.4 minus 1 1.4. So T2S is T2S T2S is 530.75. Then from T2S we can get T2 equation. The formula for T2 is, and efficiency for compressor is actually T2S minus T1 over T2 minus T1. We have this, we have this, we have this, we have this, and we want to find T2. So T2 equals to T2 equals to 566.27. Okay. We have this, we have this, we have this. So for the next few parts, I will skip the calculation, because I'll tell you which information we have, and you can do the calculation yourself. So next we have T2 ready. Now we want to find T3. We know T3 is 1073K, so we get from the graph already. Now we want to find T4S. It's the same T4S, 4S over T3 over T4S is actually 8, which is the RP, 1.4 minus 1, K minus 1 over K. So we have want to find T4S, we have T3, T4S equals to 1073 over 8 to the power of 1.4 minus 1 over 1.4. And we know T4S is 592.34. Okay. We have T4S. Now we want to find T4. It's the same like this. We use the isentropic efficiency to solve. And efficiency for turbine is T3 minus T4 over T3 minus T4S. We have this, which is 0.93. We have this, and we have this. So we want to find T4. T4 is equals to 626 K. Okay. So we have the basic 4 points, and now we want to find T5 and T6. Okay. As from the question, we know the T4 is slightly higher, which is 10 Kelvin, than T5, which is inlet temperature for regenerator. So we know, and applying first law to regenerator, which is T5 minus T2 equals to T4 minus T6. Okay. So we know T4 minus T5 is 10. So we want to find T2. We have T2. We want to find T6. So T6 equals to T4 minus T5 equals to 10. T4 is 626. T5 equals to 616 K. Then from this, we solve the equation. T6 equals to T5, T4 minus T5 plus T2. We have this, so we know T6 equals to 10 plus T2. T2 we have 566, 127. So T6 equals to 576.27 K. So we have all the points now. I'll list it down. And because for the next part, you want to solve a question, my partner will explain to you how to solve the question. So I'll list down everything.
Hi, I'm Heng. My full name is Lim Yu Heng. So today I am going to explain the next two questions, which is the mass flow rate and also the heat addition and heat rejection. So the first thing we have to find out is for the mass flow rate, right? Because after all this calculation, so we have to find out what's the efficient work of the turbine and the work of the compressor. So work of the turbine. How will we solve this question? Actually, this question very easy only. So we just follow the formula, the constants, and then turbine is over here, 3 to 4. So it's T3 minus T4, right? So I directly put the answer because we have a lot of the point over here. We have CP, which is constants 1.005 from the table, and T3 is over here, T4 is over here. So it's okay, I just write down the things 1.005, and then T3 we got 1073, and then T4 is 626. So final, we can get the answer is 449.24 kilojoule per kg. So as we can see, we can get the work for turbine, and then afterwards we will move on to work of compressor. So the part over here is turbine, so the part over here is compressor. So we get to know that compressor is over here, so it's T2 minus T1. T2 minus T1. The similar things we get for the constants for the CP is from the table also, so which is 1.005, and then T2 566.27 minus 293. So we get the answer is, after we solve the question, 274.6 kilojoule per kg. So as we get the work of turbine and the work of compressor, so what should we do now is we have to take the work output, the work net output. So the formula for the work net output is work of turbine minus work of compressor. So it's just like you take this one to minus this one, then you can get work of net. So the work of net finally we can get is 174.64. Okay, so can you get it? If you can't get it, you just refer back to the previous video. Okay, so now we have the work net. So now we have to find out what is the mass flow rate. So actually we have the W dot net over here, the rate of work over here, and we have the work output over here. So it's actually very easy to solve this question. It's like you get the formula from the slide. Okay, so the formula is actually like this: the rate of net work is equal to mass flow rate times with the work output. So how you're going to find this is just like your rate of net work divided by this. So you can get the mass flow rate is equal to 0.86 kilogram per second. So this is the answer for mass flow rate. So next, I'm going to explain about the heat rejection and heat addition. So I'm going to rub this. Have you taken note of this? Okay. So now we have to find out the heat rejection and heat addition. Sorry. So as we can see in the graph over here, Q in is represent heat addition, and Q out represent heat rejection. Okay. So how we solve this question? QE. This one is heat addition. Heat addition. So how are we going to solve this question? We have to find out the constant also. And then from this, we just take T3, the temperature of 3 and 5, minus 5. So settle. Right? For the heat addition. So we just always refer to the graph only. So we write down the answer is 1.005. And then what's T3? 1073 minus 616. 616. So what do we get? 459.29. 459.29 kilojoule like kilogram. Is it correct? Okay, so we move on to the next question. Not to say the next question, we move on to the heat rejection. How are we going to find out the heat rejection is Q out. Heat rejection. So how? It's the same formula. You have to put in the constants, the specific heat, and then from this graph, as we can see, this one is T1, this one is T6. So always take the higher one to minus the lowest one. So which is 6 and 1, right? So we just write down T6 minus T1. Those same things. Constant specific heat 1.005. T6 is 576.27 minus 293. So the final, what should we get? The answer is 284.69. 284.69 kilojoule per kilogram. So that's all from this question. So I'm going to invite my friends to explain about the next question. So maybe more in details. Thanks.
Yeah. Rate of heat and rate of heat.
That's not great, right?
这个只是 Q out 吧，然后乘进去 M dot 那边。
还要乘进去 M dot 啊？
因为我只是写一下就好，因为我觉得只是。
哦，直接啊？
你要直接写。
哦 rate， 哦
rate of
OK。
heat addition。
对啊
然后乘进 M dot。
你對有啲啊？
喂，
跟住。
嗰時
你對有啲？我點呢？record 呢個啦，record 啊，record 呢個。So I'm sorry for that. For Q in is actually.
Okay, come again.
Okay, I'm sorry for that. So actually Q in is the heat addition and Q out is the heat rejection. But the question asks, the question need the rate of heat addition and heat rejection. So we have to add on the mass flow rate, which is we found just now is 0.86 kilogram per second. So how to find out the rate of heat addition and heat rejection is heat for heat addition is Q dot in is actually equal to M dot times Q in times the heat addition. So what we can get here is, I'm calculating, 394.99. 394.99. And then for the Q dot out for the rate of heat rejection is equal to mass flow rate times the heat rejection. So what we can get is two, 4.83. So actually, this one is not yet finished because I not yet put in the units. So what's the units? Kilojoule per second. So don't forget the units, and you will lose the marks. So that's all from me. Thank you.